So have you ever asked yourself how self-driving cars actually work? If this is the case, then this lecture may help you to understand what are key building blocks of self-driving cars and what needs to be done in order to give the capability to drive autonomously to those vehicles. So it's a course that I'm teaching here together with my colleagues Behley, Nived, Chebrolu, Benedikt, Mersch and Igor Bogoslavskyi, trying to give you insights in how autonomous cars work, discuss with you current related work in a seminar, and also support you implementing certain building blocks of self-driving cars on your own. So it's a new course that we are teaching in the upcoming winter term here at the University of Bonn. I hope you will enjoy those lectures, at least for those of you who look that over the internet on YouTube. Enjoy the video lectures here and stick with us towards the end of that course so you will learn something about autonomous vehicles and get an understanding what techniques are used when realizing self-driving vehicles and how key building blocks can actually be realized. So again, this is the first introductory lecture of a block or series of lectures that we are giving here, which are accompanied with the seminar as well as with project work. So let's start out with answering the question, what's actually a self-driving car? So a self-driving car is basically a regular car that has been instrumented. And instrumented here means we typically equip those vehicles with sensors so that they're able to perceive their surroundings. This could be a 3D laser scanner, a camera, a GPS, IMU, are for example typical sensors that we put on autonomous vehicles. Then those vehicles have computers on board and they process the sensor data and turn this sensor data in relevant information into models about the world in order to estimate what's going on and what happens in the future. So that they are then able to derive steering commands, that means the steering angle of your steering wheel and how hard you push the gas pedal or the brake, and send this to the vehicle. So the vehicle can be controlled by a computer, also requires typically some instrumentation, so that you can from a computer set the steering angle and how hard you press the gas pedal or the brake. And this then allows the vehicle to navigate on its own. So the key question is, which kind of motion commands should we execute in order to react appropriately to what happens in the world. And what you see here on this slide are a couple of examples of self-driving cars. So this was Stanley, the vehicle that won the DARPA Grand Challenge, developed by at Stanford University around Sebastian Thrun and Mike Montemello. Then bring that a step further, they joined Google and built the Google self-driving car. This is Toyota Prius here on one of the first public demonstrations around 2009. Then Google has pushed autonomous driving forward with a vehicle, so it was around 2014, where you can see already the evolvement more towards beautifully designed vehicles that you may be able to sell at some point in time, hopefully. And finally, a concept vehicle also by Waymo, now even one without even a steering wheel on board. So this is full autonomy that you as a human can just sit inside the car and you don't have to care about what the car does, what the traffic situation is anymore, and can drive on your own. So we are not fully there yet in the sense that this works in all situations, but we are making substantial steps as a community forwards towards self-driving cars. So now you know what self-driving is about. Now we want to talk about what the aim of this lecture is. So we want to give you here an introduction to self-driving cars and let you understand what are basic techniques that are used in order to realize those vehicles. So we look a little bit into key building blocks. Of course, we cannot address all building blocks that are needed in order to build an autonomous car. We just take a subset of them and then try to give you hands-on experience on how to actually realize such a component. So this involves you programming building blocks of those autonomous vehicles that you then are either able to test them on real-world data that was recorded with the vehicle or based on a simulation system. So testing especially the active and planning and control algorithms in simulation. So we want to also give you a perspective here, not only from the academic side, because we are at the university, we are academics investigating autonomous driving and how to develop new algorithms for this, but we also have a speaker who is in industry and wants to provide you with an industry-related view to autonomous driving, so more a view from practice. And We again try to do this as a combination of lectures, project work, and seminar work, so that you also get an idea what are current state-of-the-art approaches, what is discussed today on conferences, and what is, again, the current state-of-the-art. What we assume here that you have some experience in robotics, photogrammetry, state estimation. So the lecture that I've been teaching here in the last semesters, or also video lectures that are online, mobile sensing and robotics, for example, all the photogrammetry courses are component that we build upon. So we assume you have basic knowledge, for example, in state estimation, because localization, as an example, will not really be addressed here in this course, although of course it's a key component in self-driving cars. So we have to focus a bit on a subset of components. So in order to say what kind of components do we want to have and what should actually be realized, we need to first understand what a self-driving car needs to do in order to navigate through the environment. So what are the key steps that self-driving cars need to realize? So first of all, self-driving cars must have the right prior knowledge in hand in the right way that it can be exploited and can be combined, for example, with state estimation techniques. So what does that mean? For example, you need to have a map of the environment. Most of autonomous vehicles require a map of the environment in order to plan the path, in order to, for example, localize them precisely where they are on the road, in order to understand which areas are drivable areas, which are potentially non-drivable areas. So some prior knowledge typically has to be provided. Then the system must estimate its own state. So where am I in the world? This can be done via GPS, of course, but you may want to relate that also to the map information that you have, so that you can precisely localize yourself in the map, can deal with GPS outages or failures of individual sensors. So you must estimate your own state as well as the state of the object around you. And this is where we go towards the perception side. So you need to use your local sensors to perceive your surroundings on the one hand side to help your own state estimate, but also to estimate what other people are out there. So where are other cars? Where are obstacles? Where are traffic lights? And you need to understand what's going on in here. So you need to, for example, perceive another vehicle. You need to know that it is a vehicle and not a cyclist or a pedestrian, for example. So you need to develop algorithms that can distinguish those objects from each other. If you have that information, then you typically want to make prediction about what's going to happen next, because the car needs to be able to predict, let's say, 5 or 10 seconds into the future what is likely to happen, what are different possibilities, how other drivers may react, because you need to take these potential actions of others into account in order to navigate safely through the environment. This is what we typically refer to as prediction, so we want to predict what's going to happen. And then the car needs to think what it should do. So it needs to reason what are appropriate actions, which actions are safe and will not lead to collisions, which are actions that lead to maybe a perceived safety or comfort in driving, or guide the user to the target location as fast as possible. So there are different objectives that need to be taken into account when deciding what to do next. And then, of course, the car needs to execute those motions and make sure that the vehicle actually executes what the car commanded or what the computer commanded the car to do, and need to monitor the plan execution and run this perception prediction loop over and over again. So again, there are key things we need to do. We need to have prior knowledge. We need to perform state estimation. We need to perceive our surroundings and interpret what we see. We need to predict what's going to happen next. We need to plan and then to act. So to execute our plan, in this sense, our steering commands in order to come closer to a desired state. So I also brought you a few examples how that can look like on a real autonomous vehicle. So this is image material from Waymo. So what you see here is the view of a camera put on top of the car of the street surroundings, and it always overlays with the current estimates that are ongoing. So what you first need to do, you need to know where you are, so you need to know your pose, and exploit map information, like, for example, a label here of those crosswalks. You need to know where potential traffic lights are, and different information that are stored in a map of the environment needs to be taken into account. You need to relate that to your own state estimate. So that's the first thing that you need to do. The next thing you need to do, you need to perceive what happens surrounding and also estimate the state of other vehicles. So you need to be able to say, okay, this is a vehicle here, this is another car here, this is a pedestrian, there's another pedestrian over here, this is a vehicle, this is a vehicle. And here's a traffic light, that's a traffic light, this traffic light shows red. So this is information that you need to perceive and integrate into your model, into your using state estimation approaches and machine learning techniques to interpret what you're actually seeing. So by now you have assessed the current state of the world, your state and the state of all agents around you or other vehicles, traffic participants around you. The next thing you need to do, you need to predict what's going to happen next. So in order to predict what's going to happen next, you need to have the state of those other objects available. So you need to know how fast other cars are driving, where they are precisely in the world. Also take maybe into account on which lane they are, so integrate that with map information. And then you need to predict what's going to happen next. And often this is a multimodal prediction because you cannot exactly say what's going to happen next. You may say, let's say 30% probability the car will turn right, and with 70% probability the car will go straight. So you will have these multimodal beliefs about potential actions that other traffic participants will do. And this typically requires machine learning approaches. So those systems typically are a combination of rules and learning approaches trying to predict what other drivers are doing in order to have an idea how the world may look like in 5 seconds, so that the vehicle can then plan its path, taking these predictions into account and try to find trajectories which minimize the risk of collision, which minimize risk of behaving illegal on the street by doing illegal driving maneuvers, for example, but also giving the user a pleasant driving experience. And then the system, after it has planned its path, it of course needs to execute those actions and need to plan a path like this path over here, how it wants to steer through the environment and then execute that path. That means make sure the vehicle actually drives on that trajectory by sending the appropriate steering commands to the vehicle and monitor how the vehicle is actually executing those commands in order to take corrective actions, for example. So these are the key building blocks that you need in order to realize an autonomous car. In this course, we cannot look into all of those building blocks, so we'll look into kind of 2 topics or 2 areas here. The first thing is perception part. So it basically means making the car see. So in order to understand what the car sees, what are objects that are around me. And the second part is the control and planning part in order to compute a trajectory, how the vehicle should behave, and then also use the control commands in order to make sure the car actually follows this trajectory. Again, this is just a subset of the possible tasks that an autonomous vehicle needs to do, but given the size of this course, we need to restrict ourselves to a few building blocks. That doesn't mean that the other building blocks are less relevant. So, for example, making prediction what's going to happen in the next 10 seconds is still a very active research area and a very important task that needs to be solved in order to build autonomous cars that drive safely through the environment. But again, we need to restrict ourselves here a little bit. Okay, before we want to dive actually into the techniques which are out there, I want to give a brief history of self-driving cars. So most of you may think that self-driving cars is something that started maybe 15 years ago, but that's actually not true. So the idea of self-driving cars, at least, is around 100 years by now, a bit more actually. So in 1918, the Scientific American describes for the first time the idea of having a self-driving car, in the sense a car where you only need to sit into the car, press a button, and then the car drives on its own. So the idea of self-driving cars is around for quite a long time, although the technical developments towards self-driving cars came later. Nevertheless, 3 years later, people developed the first remote-controlled car, or radio-controlled car. That is, of course, not a self-driving car, but it's already a very nice demonstration how you can go towards having not humans inside the car, but of course you still have the human operator which steers the car. So it's not really a self-driving car. And then for the next years or next decades until from the 1930s to the 1970s, 80s, there were several predictions of how self-driving cars would change the landscape, how great it would be to have that, and people were predicting that those vehicles would come actually quite soon. It, however, took a while until 1977 when the first street vehicle was built that could drive autonomously. This was done in a lab in Japan by Tsugawa et al., who modified a street vehicle with cameras and were driving up to 20 miles per hour on a closed road and could show that they can use sensor data and generate basic motion commands in order to drive with a vehicle. Then around 85, DARPA launched the autonomous land vehicle. This was also a camera and LiDAR controlled vehicle that could drive on a path and then stop at a certain point in time, so showed basic navigation capabilities. What I want to highlight here is the Eureka project by Dickmanns. So Dickmann was a professor at Munich at the Bundeswehr University, the University of Forces in Germany, and he was one of the pioneers in autonomous driving, bringing autonomous cars on our roads. And over a decade or longer, he has made groundbreaking research in order to build those vehicles in a time where mobile robotics, for example, we're still not far from the state they are today. Also in 93, 94, Bosch and Toyota built a vehicle that could detect lines or lane markings and follow another vehicle. And then in 94, this was basically one of the final demonstrations of this project. The Prometheus vehicle drives for 1,700 kilometers from Munich to Denmark and back on public roads, which was a big success at that time. Even if you compare it to autonomous capabilities that cars have today, it's remarkable what those researchers did. And then followed in the end of the 90s demonstrations of longer rides and even public demonstrations with autonomous vehicles in San Diego on the interstate, or around San Diego on Interstate 15. So there have been autonomous vehicles and demonstrations out there yet, although they didn't receive, or not all of them received the attention that they probably have deserved. And I want to show a few examples of historical vehicles, so the first street vehicle, and then a video about the achievements that Dickmanns have done. So I couldn't find that many information in terms of video material, but I found this image that showed this instrumented vehicle, again, that was able to drive around 20 miles per hour using a camera to observe the road in front of them and then perform basic steering commands. So the first vehicle that was instrumented and was used to realize autonomous driving. And then a few years later, Dickmann had a great success with instrumenting a vehicle with his work at the Bundeswehr University in Munich. This was this Mercedes-Benz bus that was completely instrumented inside and was using different sensors such as cameras in order to film the road in front and generate the appropriate motion commands. And this has led to drives of that vehicle of more than 1,700 kilometers from Munich to Denmark and back, and also drives involving France in Paris. So they did great achievements with their vehicle. I also brought a small video showing that system of Dickmanns.
Autonomous road vehicle guidance.
The test vehicle, VAMORS, seen here, has been in operation since 1986. This period was preceded by 8 years of preparatory developments, with different types of simulation culminating in the real-time simulation loop. Based on data fusion from various sensors, the onboard computer system automatically controls the steering wheel, the gas pedal, and the brakes. The direction the cameras are pointing may also be controlled by computers. In 1987, VAMORS demonstrated worldwide top performance on a new stretch of Autobahn not yet turned over to the public. It cruised at various speeds with top speed of 96 kilometers per hour, limited only by engine speeds, over a distance of more than 20 kilometers. Since 1989, it has also been possible to recognize obstacles. As a consequence, it has been possible to achieve the transition into a convoy driving mode. Since the early 1990s, it has also been possible to perform lane changes autonomously. In 1993-94, in the framework of the third phase of the Eureka project Prometheus, 3 Mercedes-Benz S-Class passenger cars were equipped with University Bundeswehr vision systems based on new micro-miniaturized TV cameras. All electronic equipment now fits into the trunk space in order to achieve better maintainability and accessibility. However, in the UBM vehicle VAMP, part of it has been mounted on the right back seat. Up to 6 other vehicles may be tracked in parallel in both the front and the rear hemisphere. Their state relative to the Igor vehicle is estimated concurrently at a rate of 25 Hertz. On this basis, at the final demonstration of the Prometheus project near Paris in October of 1994, on a 3-lane freeway with normal traffic, the capability of making the decision for lane change fully autonomously was shown for the first time. A module developed by our computer science partners at UBM tracks the entire traffic situation around the vehicle, especially in the neighboring lane to be changed to.
So after having seen the great capabilities that Digman has shown already in the 80s and 90s, it's very remarkable where we are today, and this vehicle, of course, was only a demonstration at kind of small scale compared to what we have seen today with car companies driving millions of miles autonomously, but nevertheless it was a great achievement at that time. And since 2000, autonomous driving has accelerated substantially. So one of the key events was the DARPA Grand Challenge in 2004, where DARPA announced the prize money for building an autonomous vehicle that could drive a certain distance, and mainly off-road or desert road driving. And the 2004 DARPA Grand Challenge could not be won by any of the participants, but it was the event that stimulated a lot of research activities on autonomous driving in different communities, for example, the robotics community. So a lot of teams generated or started investigating into autonomous driving, and it led to a boost in building autonomous cars. This has led then to the DARPA Grand Challenge 2005, where Stanley, one of the vehicles that I've shown on the first slides, won the DARPA Grand Challenge and finished the race as the first one, as the fastest vehicles. And this was kind of a starting point for several startups being created, trying to enter the autonomous landscape, partially performing navigation tasks like whatever, or navigation tasks and also mapping tasks. For example, Street View, or the acceleration that Street View became so popular, also depended on the development of autonomous vehicles that use the sensor technology in order to perceive the surrounding and build models of the surroundings. DARPA also launched an urban challenge in 2007, where the driving was done in a city environment, or in a mock-up city environment, and where also other traffic participants are involved, and the cars had to respect further street rules in order to navigate through the environment. And at that time, after 2005, a couple of researchers actually went into companies building autonomous cars, founding startups, and the very popular one, or most popular one in these early days, was probably Google, who was working under Sebastian Thrun on autonomous vehicles. And in 2009, they made the first public demonstration of their autonomous Prius vehicle, showing it to the press, showing how that car was able to drive. We'll see a video about that later. This has also led to further developments. For example, the Stanford race car was used to drive up very fast Pikes Peak, so a mountain road in California, showing impressive results. And all those developments of having public demonstrations showing what the potential of those self-driving cars were also has led to a substantial increase of funding. So from around 2013 on, the funding that has been put into autonomous driving increased substantially. until it peaked around 2017. And since 2017, it kind of has stagnated a little bit or is kind of constant, and certain consolidation actions take place. So a lot of companies realize that it's actually harder than they thought to build autonomous vehicles. We see a lot of large players also building joint ventures or fusing their efforts in order to build autonomous vehicles, because it turns out that bringing the vehicle actually to the road was more tricky than originally seen or estimated, so that a lot of companies now team up in order to build autonomous cars that can actually be bought by customers. So on this plot here, we can nicely see the development of the funding that was put into autonomous driving. You can see here it was fairly little in 2004, 2005, and then increased around 2006 after the DARPA Grand Challenge, and then went up. And then from 2013 on, the funding increased substantially, reaching its maximum peak of $40 billion, or more than $40 billion that has been put into autonomous driving developments, funding companies doing autonomous driving, and now has stagnated between 30 and 60 billion per year. And that's where we are right now in 2020 over here. So no final numbers for 2020 available by now. So the question is, who got all that money? Who are key players out there in the field? And there are a large number of companies, or a substantial number of companies out there in the autonomous driving landscape that build autonomous cars. So a few of them I have listed here. So very prominently is Waymo, a daughter company of Google, or a spin-out of Google, so one member of the Alphabet group, that built autonomous vehicles from the early days on. So started maybe around 2007 with the first public demonstration in 2009, and is also one of those companies which have probably driven the most amount of miles in an autonomous fashion today. Uber, also very known, also has been in the press in the recent years for their developments on autonomous driving and for building autonomous vehicles. Also one of those key players, also having substantial collaborations with university partners in Toronto, for example. Uber founds an own lab for research on autonomous driving. Tesla Motors is also one of those players who has sold probably the largest number of cars that have autonomous capabilities. So the Tesla series cars have the Tesla Autopilot, which can do certain maneuvers in automated fashion. And maybe the special thing about Tesla is that they only rely on camera data. So the Tesla vehicles don't have a LiDAR. I mean, of course, they have other sensors except of cameras, but they explicitly not use LiDAR data that most of the other companies do in order to estimate the distance to obstacles. So that's something which is special here. Apple Project Titan is also development for autonomous cars. The number of autonomous cars that they have out on the road is smaller than other players, such as the Waymo, for example. And it was everything very secret about Apple Titan in the spirit of the company. Then there are other companies out there, such as Lyft, Level 5 driving, Oxbotica, also a company that was spun out from University of Oxford, around people around Paul Newman and Ingmar Posner founded Oxbotica as a company to realize autonomous driving, and are one of the key players in the UK today. Apex AI as well, one of the companies funded 3 to 4 years ago, working on software for autonomous driving stack, trying to provide safe navigation, safe communication infrastructure that is compatible with what a lot of people use in robotics, and providing an own operation systems for autonomous behaviors. Argo, who has recently fused or acquired autonomous intelligent driving, company originally owned by Volkswagen, now owned by Volkswagen and Ford together, located Pittsburgh, but also offices in Munich. Toyota, or TRI, Toyota Research Institute, is also one of those key players. Currently Wolfram Burgert involved in that endeavor, realizing autonomous driving at Toyota. Also Toyota is a company that has invested a lot in collaborations with universities. University of Michigan also has played a key role in the developments of the technology at Toyota or TRI, so also seeking to a lot of interactions with the universities. Daimler and Bosch have recently, or have fused their activities on autonomous driving. Again, one of those two big players working together towards building autonomous vehicles. GM Cruise, similar to this, also one of those players who are bringing miles out on the road today and pushing the boundaries of autonomous driving forward. Baidu Apollo project is a more younger development, but also has shown impressive capabilities in terms of their disengagement rates. So how often does the driver need to abort the autonomous driving capabilities? So they are also, together with Google, one of the key players in here. Then there are a series of other companies out there working on autonomous driving, also with substantial personal effort, like Aptiv, and also a large number of other companies which are out there. Just to kind of give you a rough idea which players are out there in the field and where we stand today. Okay, so the next step is, and this is also related to some of the activities that the companies are doing, what does actually self-driving mean? So if we talk about self-driving cars, what do we actually refer to if we say self-driving? Is this an advanced autopilot? Is this full autonomy without any human in the loop? That is actually something that we need to distinguish. And for that, there is a classification of so-called levels of autonomy. So there are different levels of autonomy of autonomous vehicles that describe which functionality the car actually provides. So it starts with level 0, which basically means no automation at all. So your traditional old school vehicle, up to level 5, which is full automation, which basically means in all situations, the driver is not required anymore. The system can drive completely on its own under all conditions, no interventions by any human. And of course, in between, we have all levels where we partially need to have the driver on board, or even where we don't have the driver on board anymore, driver paying attention to that. It starts with basically driver assistance, going towards partial autonomy, and then conditional autonomy, so where the human is still required, but a lot of even safety critical maneuvers are executed by the car, towards level 4, which is basically autonomous driving, but not in all situations. So for example, in a snowstorm, the vehicle may say, I'm not able to drive right now. Either the user has to drive or the vehicle can't drive. That will be kind of level 4 autonomy, and level 5 would then be drive under all conditions. So level 0, again, no automation at all. Level 1 is basically basic steering and acceleration tasks. It's basically driver assistance systems that we see today can be seen as level 1 autonomy, where the car controls certain functions on its own, but you as a driver are in the driving seat. You are responsible for what's going on, and you have to monitor the road at all times. Level 2 can be seen as kind of an advanced cruise control, where you as a driver are still responsible, you still need to be alert, but the vehicle does certain maneuvers such as accelerating or braking on their own. So it's kind of, let's call it an advanced driver assistance system. Advanced cruise control is what we would refer to as level 2 autonomy. Level 3 autonomy is some kind of a special situation in here where safety critical functions are already executed by the vehicle on its own, but the driver is still required. So the human still must be there and pay attention. The problem with level 3 autonomy often is that the system is already quite good in what it does, so the human will actually not concentrate on the driving situation. And as a result of this, although the system runs autonomously in a lot of situations, and the human will probably not pay attention anymore, the human is still required to take over. And therefore, level 3 is something that is currently not in the main focus today, because it's very tricky to realize this combination of autonomous vehicles and having the driver being alert at all points in time. Therefore, level 4 is currently the next step for most of the companies out there, where we have autonomous behavior in almost all situations, but not in all situations. So you may restrict the autonomous driving behavior to, let's say, certain weather conditions. So if there's pouring rain or a snowstorm, you may say autonomous driving is currently not available, or you're restricted to certain parts of, let's say, a mapped area, to highways or to certain parts of a city. That would be kind of level 4 autonomy. And then finally, level 5 autonomy, we say we can drive under all conditions, no human required anymore, no steering wheel needs to be in that car. That would be level 5 autonomy. And if you look to most of the developments we see today, most companies either focus on level 2 or level 4 autonomy. Of course, with the final goal of achieving level 5 autonomy, but what they're currently working on. So level 2 basically as an intelligent driving assistance system, and level 4 as kind of this next step towards a full self-driving car, actually stepping or ignoring this level 3 autonomy. And most of the interesting things happen here in this level 4 with the goal of heading towards level 5 autonomy in the developments of autonomous vehicles over here. So the question is then, how long can a car actually drive before a human needs to step in? So how long can those cars actually navigate through the environment before a human needs to take over the steering wheel? And that's something that can be measured, the so-called miles per disengagement. So how many miles can you drive before the human needs to step in? And if you're an autonomous driving company and you work in California, you have to report every year numbers. And some of those numbers is how many miles you have driven, but also the miles per disengagement. And you can see here that this varies dramatically between companies. So we see the companies, the miles driven here from 2,000 miles to 18,000 miles. And you see that there's just a small number of players, 4 to 5 players, which are actually able to drive a substantial number of miles before the next disengagement happens. Their key players here are Baidu with 18,000 miles, but also Waymo with 13,000 to 14,000 miles and before disengagement takes place. Our key achievements are real milestones in autonomous driving, where other companies really go down to much lower levels. And so there's a small number of players which reach those high rates and also driving a lot of miles. So again, a disengagement is whenever a human takes over the control. So either steps on the brake because the car does a dangerous maneuver or makes a steering command, or aborts the autonomy for whatever reason has happened. And this miles per disengagement gives you an idea how long a car can drive on average before a human needs to take over control. And of course, we want to bring that up to very, very high values if we want to achieve level 5 autonomy. So how many miles do autonomous car companies drive? This is actually something which is not always easy to assess. But again, for the miles driven in California, this needs to be reported. So alone in 2019, Waymo, for example, has driven nearly 1.5 million miles with their autonomous vehicles. And then GM Cruise approximately half of this. And this, the number is going down, that except of Waymo, Cruise, Pony AI, and Baidu, none of them has driven more than 100,000 miles in California in 2019. So again, these are only numbers for California. If you are in different countries, you may not need to report this. All those numbers are at least not public. So it's hard to judge this and or generalize this, how it looks like worldwide for those companies. So those 4 players over here, I've shown here some of the example vehicles by Waymo, for example, the Apollo vehicle, Cruise, and Pony AI. And you can see that those vehicles are typically equipped with similar sensing capabilities. So you can see there are these 3 LiDAR scanners sitting over here. It's one enclosed in here. A lot of them using Velodyne 3 LiDAR scanners. They are equipped with cameras, which typically sit somewhere over here and also on the side, or further cameras here in this sensor platform there on top, also involving radar, GPS, IMU information. These are kind of the key sensors that those vehicles use. A few other examples of other vehicles which are out there, for example, by Uber. Technology is also similar, using the LiDAR. Again, the Tesla vehicle, which is one special situation here, because not situation, but special sensor setup, as they don't use LiDAR technology. They only use radar and mainly camera data in order to perform their navigation capabilities. So this is kind of a special setup and allows them to design a vehicle that actually cannot be distinguished anymore from the outside as an autonomous vehicle from a regular street vehicle. Nuro is also a company working on delivery services in the US, so last mile delivery, building also small vehicle for delivery tasks that can drive fully autonomously. And this is an example from the ARD cars in Munich used for performing autonomous driving abilities. So the next thing we want to look into is kind of what are the techniques that are used in order to realize those vehicles. So which techniques do I need to have in order to perform those different tasks, such as estimate where we are, estimate what is around us, what others are doing, planning and execution of those commands. So First of all, online state estimation plays an important role. Things like localization, where am I in the world? SLAM, simultaneous localization and mapping, which basically means localize or estimate your own pose and build a map of the environment, localize yourself in that map that you're currently building. Also, a lot of sensor fusion plays an important role. How can we leverage the different sensing modalities? Combining cameras with lasers and radars, for example, is also important problems that are investigated in this block of online state estimation techniques. Then machine learning, and especially deep learning, also plays a very important role. So how can we perform our perception? So in perception, most of the activities today are realized via deep learning approaches. For example, the detection systems, what is out there, semantic segmentation, assigning to every pixel a semantic label. Is this a car? Is this a road surface? Is this vegetation? All those interpretation tasks are typically done with learning approaches today. But it also goes further when we think about prediction, so learning how other traffic participants behave is something that is frequently done out there in order to go away from the rule-based systems, and also imitation learning. So imitating human drivers in order to come up with appropriate driving behaviors is an important task where machine learning plays a key role. In the planning and control domain, this is also a key domain in autonomous driving. Learning doesn't play in such an important role there yet. Here we're looking into path planning. We can do this on a very global scale. That's how do I reach, let's say, start here in Bonn and go to Munich. How should I navigate? That's basically a task that your sat-nav does on the very high level. But if you go down the levels, which lanes you must be driving on, and kind of how should you navigate, then it needs to take the local surroundings into account. Where are other vehicles? How do you overtake other vehicles? And they come closer to combining planning with your local perceptions and also the predictions that you have done. And last but not least, you need to actually execute the steering commands and actually make sure your car behaves as a computer wants the car to behave in order to control and build a controller that actually guides the vehicle. Again, I said machine learning plays an important role in a lot of those tasks, and we can see how much machine learning is actually involved in here. So this is a very recent slide published, I think, information published a few weeks ago by one of the heads of Nived. We can see we have our raw sensory input, and turning this raw sensory input laser data into detection of other traffic agents and doing state estimation. Here, machine learning plays a key role, and especially for all the semantic interpretation tasks. Basically, nearly everything is done using machine learning technologies. If you then use those these detections and want to turn them into predictions, predicting how the world will look like in 10 seconds, for example, machine learning also plays an important role, but also we have still a lot of rule-based systems out there because we have certain traffic rules that we can exploit. And it's so far a combination of rule-based systems and machine learning-based approaches. Going even further, if we go into trajectory planning, so taking the predictions into account in order to plan path, this is something where machine learning plays a very minor role today. We expect that to increase over the years. For example, using techniques such as imitation learning for driving could be techniques which could kind of bump that up from to higher values. But this is something that we will see what will happen here in the future. The next thing is actually what should we actually optimize for? So what is important? A few things are obvious. What is important for an autonomous vehicle? For example, you don't want to collide with any other traffic participants. So if you look into this pyramid of what is important in terms of objectives that planning systems should take into account, the biggest part, of course, is safety. So you want to stay safe. You don't want to collide with other traffic participants, for example. Then the second thing you want to make sure is legality. So you want to be in line with the street rules. You don't want to break street rules and get tickets because your autonomous vehicle is not actually behaving that well. And the third element, which is also rather important and is often overlooked, at least initially, is kind of the perceived safety. So how do a human that sits inside the car feel? So does it feel safe to drive in the car, or does it feel very awkward? And even if everything is safe but is perceived as unsafe, people will probably not use autonomous vehicles, at least at the rate as we would have them to use if their perceived safety would be great. So even if the car will not collide, but if you're driving too close to other traffic participants, this may be perceived as not safe. Then driving comfort, of course, a car kind of smooth at the right, or there are very strong accelerations or strong braking maneuvers. You actually want to minimize those. You want to go towards a more comfort ride. And last but not least, route efficiency. So you want to reach your target location fast, of course, but it doesn't matter if you reach this a few seconds earlier or later if you would otherwise violate these other objectives that are down here. So the most important one is safety, legality, then perceived safety, comfort, and the last, or least important one is actually the route efficiency. But these are kind of the typical components that planning systems need to take into account when they actually make their decisions. And they make their decisions based on what they see and what they estimate is going to happen. So the planning system, the system that optimizes for those objectives, is kind of the last element or the nearly last element before the execution itself. In the chain, it needs to rely on what do I know about the world? So what comes from my prior knowledge? What comes from my sensors? How do I assess the current state? How do I make predictions of what's going to happen? And then the things play an important role in here. As a result of this, the next thing we need to actually look into is kind of what do we see? So what information can I extract from my sensors in order to estimate the current state of the vehicles, of the other vehicles out there, my vehicle, and what's going to happen next. So, and for that we need to answer the question, what does the car see? And I want to start here with the Google car from 2009. This was, again, the first public demonstration in 2009. You can see a Toyota Prius, and the main sensor here is this 64-beam Velodyne scanner. So it's a 3D scanner which has basically 64 laser beams which is rotating and perceiving the world around it with 10 hertz, so 10 times per second you get 3D view or 3D point cloud of your surroundings. And this is how such a point cloud would look like. You can see here the sensor in the middle, and you can see these circles around the car, concentric circles. These are basically the point cloud in the 3D world on the surface. Also kind of from the curb here, you can estimate where the street is. You can probably estimate that these are buildings, probably some vegetation here in front. So this is the kind of data that the car gets at the raw point clouds. It's a raw 3D LiDAR scan projected into the 3D world as a point cloud. And what we need to do if we see this, we need to interpret what we are seeing. So we need to interpret that this is a road, that this is our lane where we want to go, and that there are other traffic participants around. So we need to interpret what's going on there. And that's something, an example that we see here also from around 2009. You could see the vehicle over here. You could see in green here, so the color is basically the altitude. You can see objects sticking out. These are other cars. These are pedestrians. These are cyclists over here. And you see some of the vehicles with those pink bounding boxes. These are cars which may potentially interfere with the desired or planned trajectory of the vehicle based on their movement on this intersection. And that's basically what the car sees, or state of what the car saw around 2009. And based on this, making decisions of what to do next and then executing those decisions. So there's a nice video which shows the first public demonstration of the Google vehicle driving with this Prius on a parking lot on a predefined track, having journalists on board. And I just want to kind of start showing this video as kind of the first public demo of this vehicle.
Thank you.
All right, we're about to take you on this self-driving car.
All right.
Google.
We hope we're still alive at the end of this.
Yes.
We're trusting our lives to you, Andrew.
Oh, thanks. It's not me.
Yes,
What,
I
you
hope
filming me, filming you?
When you
Yeah.
filming me?
Filming me? Sorry.
so there are no
You hold
bugs,
this.
right?
Oh, I gotta hold the
We
keyboard.
have lots of unitaxis.
Here,
Yeah.
Harry, you trust me?
I trust you.
Control Alt Delete.
Here we go.
All right, so my hand's near the wheel and my foot's near the brake, but I'm not touching it.
Oh damn! Oh, mother! Shit!
Go to the left.
Holy shit.
That was a cone.
What? I can't.
Yeah.
We nicked one?
That's the second cone we've nicked.
Yeah.
So you're not accelerating at all?
No. I think we nicked one. I think we got it. Oh, much obliged. All right, and that's the finish line. It'll slow down.
Wow.
Manual.
Okay, that was definitely
We went back to manual, so we're on automatic.
in manual mode.
Wow.
What's the highest we hit?
45.1.
You get to the point where you can actually just talk to the car and have it say, just say drive.
You just push the button.
Oh, or you could,
Is that too hard?
you could do that too.
Yeah.
Yes.
It is actually.
I want to make it that easy.
That's awesome.
Thanks a lot.
Yeah, thanks. You want to go?
Do it.
Here, I'll give this one back to you.
Oh my gosh. Did you smell the burned rubber?
Smell the burn rubber.
You're going back in.
Hell yeah. Awesome. I'm gonna go front seat.
Okay, so what we've seen here that the car was able to drive on the parking lot, not faster than a human would do it, but probably driving maneuvers which seem to be of very high acceleration for the participants in there. So there's something that the perceived comfort that we have shown a few slides before may not be optimized for, but still was a rather safe ride. There are other companies out there who build autonomous vehicles driving on public roads. And I brought you another example, in this case from Oxbotica, showing how those vehicles navigate through the environment, just kind of showing this video, giving examples on how this navigation looks like. Then we can even go a step further and look how it looks from the sensor point of view. So what you see here is a camera on one of the Oxbotica vehicles. You see the kind of sensor setup, the LiDAR scanner Velodyne sitting over here, taking 3D scans of the environment, other sensors equipped here, over there, perceiving the world and turning the perceptions into predictions and then into steering commands. And when we then look into those perceptions, we can see what the vehicle actually perceives. So what you see here are 4 examples, also partially recorded in Germany, from the Oxbotica vehicle, where you can see the raw camera image, always shown kind of in the first row over here. In the second row, you can see the semantic interpretation. So different colors refer to different semantic classes which are out there. And then the lower one, you kind of see the camera image overlaid with the 3D point cloud that is actually estimated from a learning-based system from the camera image. So being able to infer the depth information based on the camera information using learning-based approaches, so that you can reduce the need for LiDARs, for example, more go towards the use of camera. So it also estimates depth information from the camera. So once you have those perceptions, you can actually turn them into a different view as well. This is basically a top-down view This is your autonomous vehicle over here. You can see the other traffic participants like pedestrians and or cyclists and other cars driving around, and basically this is the view on which the planning then often takes place. So you're basically using this information, where the other vehicles are, where are the drivable surfaces, so then that you can estimate what's going on and use this for planning. Last but not least, I want to show a video here that has been released from Waymo 2019, showing the capabilities of their vehicles.
In our early days at Google, we started working on self-driving cars. Today, we're called Waymo, and our fully self-driving cars are on the road. They use a range of technology we've built from the ground up to understand the world around them and get you where you need to go. You're about to see how it all works and what it feels like to ride in our car. As it drives, Waymo uses LiDAR, which sends out millions of laser beams per second to build up a detailed picture of the world all 360 degrees around it. It also uses radar to detect how far away objects are and their speed. And high-resolution cameras detect visual information, like whether a traffic signal is red or green. It then combines all that data to understand the world around it. For example, in this fraction of a second, it knows exactly where it is on the road. It can also identify everything around it in full 360 degrees, and then predict what those things might do next. And it doesn't just do that for the objects you and I can see. It can do that for things up to 3 football fields away. What makes everything you can see right now possible is experience. Waymo has already self-driven millions of miles on complicated city streets, and it's constantly learning from every single mile it drives. With all that knowledge, it can plan a safe path ahead. In this instance, giving that cyclist enough room to cycle past us, and also looking out for that pedestrian on the sidewalk. And when it comes to making decisions, this is a good example of how Waymo doesn't just take into account your safety. It also makes sure that both you and the people around you feel secure and at ease. So now that you know how Waymo works, it's time to take your first ride in one of our cars. Take a look around. You're now riding in a fully self-driving car. Some things might immediately stand out. The fact that there's no one in the driver's seat, no one turning the wheel, and the screens, which show you what the car is seeing and the route it's taking. But you might also notice that the ride feels a lot like being driven in a regular car. And that's the way it should feel. All this technology, which allows Waymo to see, identify, predict, and plan, should make an extraordinary ride feel completely ordinary and create a very normal journey that simply gets you from A to B, safe and sound. And while it does all that, all you have to do is sit back, relax, and enjoy the ride.
So this was an impressive example of what autonomous vehicles are capable today. And if you see those capabilities, this always kind of looks great. We can always see, wow, those vehicles can do a lot of interesting tasks. But the question is, how good are they actually? And this is actually related to the question is, how do we actually test and evaluate the developments that we do in the context of autonomous driving? So how certain are we that the vehicles that we are building are actually driving safely on our roads and that they fulfill certain safety requirements that we're interested in? And this is related to kind of how do we actually test our developments in autonomous cars? The problem that we have is that real-world testing is actually slow and very expensive. So if you need to go out with a car on the road, I mean, you have to do that at some point in time. But it's always a labor-intensive and slow testing capability. So of course you can parallelize this and not use one vehicle, use 100 vehicles or 1,000 vehicles to do your testing. So you can scale this linearly, but it's still a labor-intensive and expensive process. So one of the questions is how do we actually scale it up and do large-scale testing? Because testing may be needed very often And we also need to generate reproducible situations. Some of them may even be dangerous, or need to have the same situations if you want to test different algorithms against each other. So consider that you have several teams working on whatever prediction, for example, or on planning, and you want to test different planning algorithms against each other. Then you need to bring the car or the cars with different planning algorithms in potentially the same situations in order to perform that testing. And so if you want to test objectively, that is a big challenge. Or what are you doing with dangerous situations, especially the safety critical modules, which maybe do emergency brakes or even do braking behaviors that should minimize the impact with an obstacle. So for example, if an accident is unavoidable anymore, you may want to perform a navigation behavior that minimizes the impact, for example, on the pedestrian. And how can you actually test that? That's something that you clearly don't want to test on public roads or in practice. You may do this with crash test dummies, for example, but again, this is a very labor-intensive task. So how can we actually do that better? Another question is what happens if you implement and you change your code and you commit to your central repository and you change? Who actually tests this? Who makes sure you haven't broken up all the tests that have been done before? Do you need to send out the whole fleet of vehicles again just because you made one commit to the perception system, for example? And that is a very critical aspect. Which software has been tested? Which components haven't been tested? Do you need to rerun all tests again and drive again, collect data again, bring vehicles out on the road again? Last but not least, what about ground truth data? Especially learning algorithms need a large amount of ground truth data, and the question is, how can we actually get that data in a good way? And there are basically two ways how you can actually do that testing. The first thing is by using data sets. Of course, you can go out with your vehicle, you record the data, take the data back home, unless you're testing directly online on the vehicle, you can record the data, take the data home, and then you have these data sets. And then you can run your algorithms on those data sets. And the more data you acquired, the more tests you can actually run if you change your algorithms. But the problem is it doesn't work for all algorithms. It doesn't work for all techniques. Nevertheless, we have seen that there's much more data coming up, and they're a key building block for the development of self-driving cars. So 5 years ago, the number of publicly available datasets was extremely small, but by now the number of datasets has increased, and over the last maybe 2 years, a lot of companies also release examples, snippets of their large-scale data and start having challenges out for the community. Who can solve the best motion prediction system, for example? Who can do the best in terms of planning? So for some of those things, these datasets are really, really useful. And the more diverse datasets we get from different companies, different vehicles, the more different situations we see, the more different locations have been mapped, because driving in Germany is different to driving in the US. So you need to take that all into account if you want to build your own vehicles. And there's a large number of datasets today out there that we could use at least to test our passive algorithm. And one prominent data set which is out there since a very long time is the Kitty data set. This is an example where a vehicle was driving through Karlsruhe, recording data from a LiDAR scanner, from a camera, GPS and so on. And these data sets are out there, different sequences, and they are key tools for things like mapping. So this is an example of a mapping algorithm performing simultaneous localization and mapping using the 3D LiDAR data provided by the Kitty dataset, and you can see which maps are built from those different sequences. So this is a work done 7-8 years ago approximately. Also led to a CVPR paper, Are We Ready for Autonomous Driving? The Kitty Vision Benchmark Suite. So looking into state estimation techniques such as visual odometry, SLAM, depth from vision. These are techniques that have been tested and benchmarked against this Kitty dataset very extensively. So Kitty comes with own benchmarks where you can submit your solutions or process data on examples, and then you will be rated against other algorithms so that you kind of have an objective way for estimating how your algorithm actually performs. Of course, we can argue today that a lot of approaches have overfitted to Kitty, so just trying to get the last percentage points out of the Kitty benchmarks in order to score first. The question is, how well do they generalize to other situations? And that is something that is a true point, but with more and more data that we have, the easier this will get. There's also an extension of the Kitty datasets called Semantic Kitty. That's something that we here have done in Bonn. This was work done by my own group, the group of Jürgen Gall from Computer Vision and Sven Behnke. And what it basically provides is a semantic label for every 3D point in Kitty. So the large number of 3D scans that have been recorded in the Kitty dataset are labeled with a semantic label. And you can see with different colors here the semantic label of the point. So that this is our cars, this is road surface, this is vegetation. You can even see those kids here on the swing in real time at those red dots as the car drives by. So every point has a label, and there is also instance information available so that you can identify the different instances. So not saying this pixel belongs to a car, but you can actually break down the cars and say this is car number 1, this is car number 2, and this is car number 3. And this is an important capability that you need to be able to perform the semantic estimation or semantic segmentation, but also the instance segmentation that you can provide instance information. And that's something that the Semantic Kitty dataset provides and also benchmarks for this. But this is just a kind of a small number of those data sets. There is a large number of other data sets out there. Again, Kitty and Semantic Kitty. Then the Oxford robotic car data set is something, a development from Paul Newman in Oxford. On the way towards Oxbotica, they released a lot of the data set that they have recorded with their vehicles at the University of Oxford and released them. So you can work on snippets of data recorded over extended periods of time in the UK. The HID data set is basically a drone data set filming a highway from colleagues at the University of Aachen, or WTH Aachen, which can be used for motion prediction, for example. So these are kind of data sets which kind of come out of the academic background. There are also data sets which have been released from companies like the Waymo Open Data Set, NewScenes, PandaSet, Berkeley Deep Drive. There are a lot of data sets out there, Argoverse for prediction, level 5 autonomy data, open data, and data sets for looking on radar data, for example. So there are a large number of data sets out there, and testing your algorithm on those data sets is something that is a frequently used tool in order to benchmark algorithms against each other. So here are the links for all the data sets that I've shown before. You can go there, download those data sets, and test your algorithm with respect to those data sets. And by doing this, you already see that if you have an approach which scores well on Kitty, it doesn't mean they also score very well on other data sets, because all the different vehicles have different properties, different sensor setups, which makes it somehow different to use the individual data sets, for example, if you want to test your mapping or your SLAM algorithms. So it's actually quite hard to build algorithms which scale really well over a large set of different data sets and different situations out there. So data sets are a great tool because they provide us with real-world data. So with data which comes from a real vehicle in the real world. And we can use it for machine learning and also train our models, for example. Of course, we need to annotate that data, but once it's annotated, we can actually use this. We may also be able to use this for regression testing. That means whenever you, let's say, make a change to your perception system in the code and commit it, you can actually have a continuous integration server, another integration server, which basically downloads the code, builds the code, and tests it on all the data sets that you have available, and then provides you with a report saying you scored worse on the data sets after you commit compared to the algorithm we had before. So it's not a good idea maybe to go to continue with this one, or you may have a bug in there. So by using this automated testing based on data sets, which is called regression testing, it's a great tool to not necessarily ensure, but to reduce the risk that you commit changes to your repository which harms the performance of your system. So these are good things about datasets, what we can do with it. The bad things about it, datasets are always passive. So we only can test passive algorithms well on that, like motion prediction, like state estimation, localization, semantic segmentation. For that, it's great. But whenever we go to the active part, we can't use it anymore. We can't plan a planning algorithm on that data. Maybe just for a snapshot, for one situation, what would the car do? But we cannot take into account how would that actually be executed. What would other traffic participants do? How would they react to that plan? Because everything has been recorded in the past. It's passive. We can't change the active parts. We can't move the vehicle to a different situation in order to test how the system would behave. And that's one of the key limitations of the data set. So they're not well suited for testing with planning algorithms or generally active algorithms. Also, they provide only a rather limited view on the world. So I have situations that are recorded, I have them recorded, but I can't generate new situations easily. So we probably have the tendency to overfit to the situations we have seen so far. And it's only a limited view of the world. And of course, it's a realistic view, but in this sense also a limited view because I cannot generate new situations. And this becomes especially also harmful if you need to change your sensor setup. Let's say you already recorded millions of miles out there, and now there's a new great laser scanner out there which has twice, 3 times, or 10 times the resolution of your old data, of your old scanner. All your old data cannot exploit the capabilities of this new sensor. So how can you quickly generate new data sets that takes this new sensor into account without actually re-recording all those millions of miles that you have recorded before? Or what happens even if you just change this, the extrinsic of your scanner. So you mount the scanners somewhere else because you may want to have a better field of view, or you need to cover the space in front of the car at a higher density with your sensor data. You may want to change where the sensors are located on the car. Or even the designers who built the car say, the sensor looks very bad in here, we need to move it to a different position. Then the data that the system will generate is different from the data that you generated before. So are all your data sets invalid? Can we have tools for translating the data into new data sets which take new sensor information or sensor setup into account? These are questions which are tricky to answer and are limitations of data sets out there. As a result of this, simulation today plays a key role in the development of autonomous driving. So that means having a physics simulator that simulates how the cars would behave in simulation with other traffic participants out there. And these simulators have become a critical tool for autonomous driving. So everyone who does autonomous driving uses simulators out there, and to a massive extent. So there's one famous statement by the CTO of Waymo, say, we have driven more than 10 million miles in the real world and over 10 billion miles in simulation, meaning 1,000 times more the miles that they are driving in reality, they are driving in simulation in order to simulate how their systems behave in order to test their algorithms and optimize their algorithms. Of course, you may always ask, how good are those simulations? How close are they to the real world? That's a challenging question to answer, but nevertheless, it shows how important simulation is out there. And this is a screenshot from the Waymo's CarCraft simulation system, where basically 25,000 vehicles collectively drive 10 million miles every day. This was the state last year in 2019. So you can see how heavily used those simulation systems are. So what is great about simulations, and maybe what's bad about simulations? So the great thing is it allows us for automated and parallel testing. That means, yes, I need more computational resources, but I can actually run simulations after every commit that I have done and test key behaviors of the vehicle. I can also test the full chain, not just the perception system, but the full chain from perception up to motion execution. So I cannot only test blocks, I can actually test my whole chain, which is a big advantage. The other thing is I can also generate identical situations for different situations. So I can say, okay, I can drive on a road with the scanner having only 64 beams, and then doing the same ride with the laser scanner having 256 beams, for example. Generating exactly the same data, once with a higher resolution, once with a lower resolution. And this can be used to kind of compare how much better is my new algorithm that can use this new scanner compared to my algorithm. So I can generate identical situations with different sensor setups, which is important for benchmarking capabilities. It also allows us to focus on, let's say, tricky situations or dangerous situations. So having pedestrians that step in front of the car, which kind of emergency braking behaviors does the car realize? Here, obviously, simulations are key in order to do that in a safe way. Also very rare situations, what is out there on the road. So 95% of your data in reality is probably pretty boring because nothing important happens there and your algorithms can handle those situations very, very easily. But from the remaining 5%, they are probably 4% more challenging, and this last percent are super challenging situations. And a percent of that percent are those really critical situations that you need to master, but we are very rarely occur in the real world. And for that, simulation is great because you can explicitly focus your simulation on the tricky and dangerous situations which you cannot test easily out in the real world. And last but not least, you can use your planning algorithms to actually generate ground truth data for your machine learning algorithms. So if you, for example, have a 3D model, therefore, for every surface, you know exactly the semantic class. You can simulate range scans, you can simulate camera images that have that semantic label for every perceived point already provided. So you can actually simulate data that comes with ground truth labels, which is a great help for your machine learning algorithms because it reduces the manual labeling work. Of course, the real world is not necessarily exactly the same than the simulation. It obviously is not the case, but you're getting closer, and we're getting closer, and you are able to generate large amount of training data here. So that's all great about simulations, but simulations also have their disadvantages. So not everything simulators do is great. The key problem with simulations is they are just an abstracted model of the real world. So it's a simplified and abstracted model. It will not be able to cover all the aspects of the real world. These can be things like, are the situations actually realistic? Are the perceptions realistically simulated? What about the noise? What about outliers? What about those corner cases which can actually bring our systems to fail? Are they properly simulated in the real world? And that is tricky. And we also have to distinguish things like, oh, it just looks good from it's actually a physics simulation. So a lot of things, if it just needs to look good for video animations, for example, you have great simulators out there, but they are not always exactly physically plausible. It's not a physics engine which runs behind it, it's just an engine which makes the result look nice, which is not necessarily the same. And we need really these physics simulations in here in order to do that. Those simulation systems also need to simulate humans in the sense of other traffic participants. Is the behavior of humans realistic? That's actually something which is very hard to do because humans behave differently in different situations. They may see things and behave because of that the simulation system is not aware of. So generating realistic behaviors of humans is a challenging task. Also, are all the rare cases simulated appropriately? Has everything been considered that needs to be considered in that simulation system? These are questions which are hard to answer, and having a good simulation system is a tricky thing, or building a good simulator is tricky and a hard task to do. There are a few open source simulators out there. For this course, we opted on Kala, which is an open source simulator you find at kala.org, which we use for this course over here. So when you will be developing own components that realize a perception system or a controller, you will actually test them in the Kala simulation system. It's not the best simulator out there. There are other products which are better, but it's a rather easy to use open source simulation system which does a fairly good job, and therefore we use this here for the purpose of this course. So what Kala allows you to do is you can simulate your own worlds in Kala. So you can put in your own 3D models of a city and then simulate data from that city. It has several sensors that autonomous vehicles would have, like cameras or lidars, so you can directly simulate that data and therefore can use this for planning and control your vehicle. So if you have your vehicle, you can actually navigate that vehicle through the world. There are other traffic participants out there. They are typically, from their behavior, not the smartest ones, and just kind of drive on the road with very simple behaviors, but at least you can use it for testing your collision avoidance systems. It can be seen as kind of baselines for some autonomous behaviors. You can see if you can actually perform better ones. It's also a flexible client-server system that you can run a server and multiple clients, so you can test several autonomous vehicles against each other in the same world at the same point in time. And further, it's a rather flexible API, so you can script it quite well. Also has a ROS integration, so if you're used to the robot operating system, you can directly interface this, which is kind of nice for those people from the robotics community, because here ROS has developed into one of those standard middleware architectures. And if you use ROS already, it's fairly easy to integrate with this Kala simulation system. So for color, there are also talks out there. If you go to this website down here, you can see talks just being a few weeks old, telling you on how to use color, what you can use it for simulation. So it's a good resource if you want to learn more about that. And we will use, again, this simulation system besides data sets in order to test your algorithms that you have developed in your perception system, your planning system and controller, to give you some hands-on experience without the need of sitting in a real autonomous car. And this actually brings me to the end of this course, or this introduction here. And I hope I gave you an overview what you can expect from that course. So we will have a block of lectures covering different topics such as control, planning, perception, and so on, which gives you an idea on what techniques are behind key building blocks of autonomous vehicles and what they enable us to do. Because self-driving cars, I believe, will be a game changer in transportation industry, in the way we navigate through the world, in the way we travel in the future. So I think it's important to understand how those systems actually work. And we want to give you here a course overview. Of course, we cannot dive into all those aspects and present all the state-of-the-art systems for every individual component which is out there. But we want to give you some basic techniques in hand so that you have a capability to understand what's going on. And if you want to dive deeper, you can dive deeper. Again, we also do this for a few selected topics with seminars. We have to read papers, discuss those papers, or present those papers and discuss those papers with your colleagues in order to foster your understanding and go to the state of the art, at least for some selected topics. A lot of the perception problems or planning problems that we in the robotics community are dealing with since a long time actually very similar in the autonomous driving domain. So a lot of the developments from robotics, for example, in terms of planning can be used in there. Also in terms of perception, all the LiDAR-based perception system we have developed in robotics can be taken into account. Same holds for computer vision. A lot of especially the semantic interpretation systems coming from computer vision have dramatically influenced autonomous driving and the development of autonomous vehicles. And it's key to kind of understand the basic principle behind it. What cars need to do, they typically need to perceive the world and estimate what's going on, and they need to predict what's going to happen in the future that they can plan and act and execute their stuff. And we have basically this loop which is always ongoing, and we will look into different aspects of these key building blocks in here. So what is next in this lecture? There will be 4 more lectures here looking into control, planning, perception, and also a few from an industrial or from a practical perspective, given by Igor Bogoslavskyi, who is working for Apex AI. We will have 3 programming projects addressing control, planning, and perception, where you have to implement building blocks in Python on your own, testing them against data or against the color simulator. We will also have 3 seminar blocks where we give you papers that you need to read, that you need to present in a brief presentation showing what are the capabilities of those systems in order to illustrate what the state of the art is and what those systems can do. And of course, in the end, there will be an exam at the end of that winter term over here. And again, this is a course which is not just done by myself. Actually, a lot of work has been put in by other people from my lab. We are 5 people teaching here. So myself, Behley, Nived, Chebrolu, Benedikt, Mersch, and Igor Bogoslavskyi. So I hope we all can teach you something, that you learn something new, and can get a better understanding of how autonomous vehicles work and what they're able to do. So with this, thank you very much for your attention. I hope you stick with us and learn something interesting. Thank you.